Welcome. So our video today is calorimetry, which is the measurement of heat. What we're going to work through in our problem today, we're going to pretend I heated this block up to 80 Celsius and I dropped it into a beaker filled with water. And we're going to figure out how much heat is released by this metal block. And then we're going to ask another question, which is what is the metal block? What element is it? What material is it? Is it copper? Is it zinc? Is it silver? What is it? So we'll try to figure that out as well. You might already know what it is if you've seen some of my older videos, but don't tell anyone. All right, so that's a scenario. All right, so we're going to be searching for this property called specific heat capacity. All right, specific meaning we're talking about some specific material, heat meaning thermal energy, and capacity is how much of something you can hold or handle. So looking at the units, you have energy over mass and temperature. So that may feel a little intimidating having three different units, but I like to think of it this way. Calories is a measure of energy, so heat is a form of energy. So it's the amount of heat required to take 1 gram of substance up by 1 degree Celsius. Okay, that's heat capacity. My nickname for it is heatability. If you have a higher heat capacity, you're going to be harder to heat up. Okay, the old adage goes, it takes forever for a watch pot to boil. All right, so water has a specific heat capacity of like 1 calorie per gram degree Celsius, and whereas you study metals, they're going to be much lower. They're going to be in like the 0.1s or 0.2s. That's why metals heat up more easily. They have lower heat capacities, meaning they have easier heat ability. Okay, so we're going to look for this property to try to figure out what on earth is this metal here. Okay. So the first thing we want to do is, again, we're pretending we heated up this metal to 80 degrees Celsius, and we're going to measure how much heat is transferred when we drop it into 125 grams, 125 grams of water into this beaker. How much heat is absorbed by the water? So we're going to have to do some water-based study here. So we have this equation here, Q equals mc delta T. Q is the symbol for heat energy. We're going to use calories today. If you need joules, you can always do a conversion if necessary. Please note that the calorie today is a so-called lowercase c calorie. The capital C calorie is actually technically a kilocalorie. That's like the type you might see in nutrition facts. All right, we're working with the lowercase c calorie. All right, so calories is our energy unit. M is going to be for mass. We will work in grams. And we have our specific heat capacity. That's going to have units of calories over gram degrees Celsius. And then we have this delta T. Delta, the triangle, that's the Greek capital letter for D. In the sciences and math, we use that to indicate something has changed. And the way you track change is you take a measurement in its final stage and you minus the measurement when you first started measuring. Final minus initial. All right, so like if I had water in here and I put a hot object in, the water in there will heat up. Okay, and so that final temperature, the hotter temperature minus the initial temperature, I would get my temperature change. For my cube though, we're going to calculate delta T later for the cube. The cube cooled down, so that delta T is going to end up being a negative number. We're going to have to be okay with negative numbers. Basically, in a nutshell, if you have a positive delta T or a positive Q, that means you have heat flowing in. You're getting warmer. Okay, and maybe you'll have to learn this vocabulary word of endothermic. Okay, oops, there we go. heat flowing in if your Q or your deltaT is positive. If you have a negative number, you have heat flowing out. So your object would be getting cooler. And we would call that exothermic. All right, and you always have one with the other. So the heat absorbed, or excuse me, released by this block is going to be equal to the amount of heat absorbed by the water. Okay, this is releasing heat, so it's going to end up having a negative Q, a negative deltaT. This will end up having a positive. It's going to be the same number but opposite. All right, so that's how we go about doing the calculation, and you can see hopefully that the units cancel properly. Grams times 1/grams, that's going to be gone. Degrees Celsius over degrees Celsius, that's going to be gone, leaving us with just calories. All right, so let's hop into the problem. We're going to calculate the Q. Looks like I did that already for us, just to make sure my handwriting is good enough. But let me walk you through all the data. All right, and maybe we can just kind of write a summary list. Okay, so for our water, we have a mass of H2O of, oops, not that one. We want the 125 grams. And notice that's a mass. Like you measure water and other fluids often in terms of volumes, like milliliters, but in this problem we're needing the mass, not the volume. All right, so that's the mass, and the deltaT for the water. It can be helpful to calculate that in advance. So we went from 20 to 24.2. The water heated up a little bit. So 24.2 minus 20.0 is going to be 4.2 degrees Celsius. Okay, we're actually not overly interested in that final and initial temperatures. We're more interested in the change in the temperature. All right, and then the last thing is the heat capacity of water, and that is known to be 1, and it's actually exactly 1, because the calorie is defined based off of water. It's a water-based unit. You can think of it as infinite sig figs, 1,000. You can write just a 1, or you can write 1.00, whatever. It's an exact number, calories per gram degrees Celsius. All right, so those are the 3 things we'll need for water. All right, we'll talk about the metal cube in a little bit. This is all we need right now, how much heat the water is absorbing from the cube. Okay, so Q of water equals M water, C water, deltaT water. And now we just plug and chug. Here's our mass being plugged in, 125 grams for the water. Make sure you know which substance you're talking about. Our 1 calorie per gram degrees Celsius, specific heat for water, and then there's our temperature difference, and it becomes 4.2. All right, we are ready to calculate this, but as you can see, I kept track of sig figs as I was going through. 3, infinite, and 2. So we're going to end up with a 2 sig fig number. Okay, 525. The way it comes down to calculate is 3 sig figs, and I don't mind writing that. That's going to minimize rounding error to write all of it, but I like to use an underline to track the sig figs as I'm going through. Okay, so we're not ultimately interested in this number as much. We're more interested in figuring out something else called the specific heat capacity. So that's a specific heat for water. It's a specific heat capacity. That helped us figure out the Q. We're going to look for this same sort of information, but for the unknown metal instead. So here's how we go about doing that. I'm going to show a process. It's going to involve some algebra. Hopefully you can follow along. Admittedly, though, you might be more interested in the final result than how I get there, but I'm a believer in showing how we get there. So, all right, we are wanting to calculate the specific heat of the metal. we're going to have to find a way to get to that. So here's my process. All right, first is going to be this thought that actually, this is what I meant to talk about. Oh, much better. Okay. All right. So we want to recognize that the amount of heat absorbed by the water is equal but opposite to the heat that was lost from the metal block. So I talked about that a little bit. And the way we do that is with a negative sign. All right. So if I were to give you like $100, all right, I would have gained negative $100. All right. And you gained the $100. All right. So for my money world to be mathematically equal to your money world, I would have to put a negative sign in front of my negative $100 to be equal to your positive $100. Hopefully that made sense. But that's kind of what we're doing here, right? This water gained 525 calories. The block lost 525 calories. So you can think of it as having gained negative 525 calories. To make these two sides mathematically equal, I need to put a negative sign for whatever's there. And then we can say 525 is equal to 525. Okay, this relationship right here, okay, for the flow of heat from one object to another is equal but opposite. We're going to take advantage of this to now go to the page I was talking about earlier, right here. That's where I got that from. All right. In an equality statement like this, you can just throw the negative sign to the other side. So I throw this negative sign to the H2O side. And now I'm just going to flip the sides. So I get negative Q H2O is equal to Q metal. All right, doing some substitution, Q equals MC delta T. I'm going to make these all metal-based variables. So Q of metal is equal to the M of metal times the specific heat of the metal. That's the one we're after. And the delta T of the metal. And there's all those substituted in, still equal to the negative Q of H2O. We solved for that QH2O earlier, 525 calories, and we're gonna have the negative version of that in the calculation. So I'm just gonna move mmetal and deltaTmetal to the denominator of the other side, and this is what we get. We do our rearrangement, and then we get the C of the metal. This is what we're after. The specific heat of the unknown metal is equal to negative QH2O divided by the mass of the metal and the delta T of the metal. All right, so let me go ahead and go back to the original problem statement, and let's just make a nice list of that. So for our unknown metal, we have a mass of metal of 44.02 grams. And our delta T for the metal, we started at 80, but our final temperature is 24.2. Notice that because the water and the metal are in contact with each other, in the experiment, that means they're going to end up at the same temperature. Okay. Same final temperature. That's why I'm able to use that same final temperature for both substances, the water and the metal. All right, so 24.2 minus 80, and we're going to get a negative number here. Negative 55.8 degrees Celsius. Okay. All right, let me go back to my previous sheet. Oh, it's right here. All right, and I did some color coding here, so if you want to follow along with that color coding, I'll get that done right now. If you kind of get it, feel free to skip the next 20, 30 seconds or so. All right, M of metal, I used red. deltaTmetal, I used this magenta purple. All right, and then we have this alternate form here. If you didn't pre-calculate Q like we did earlier, if you did not pre-calculate it, you can just put everything in all at once. I know sometimes I prefer to do it this way. I don't mind doing one large calculation, so I leave that up to you. All right, but for the sake of this video, we'll just stick with finishing what we had started here. But yeah, if you want this, mass of the water was 125. I'll just draw some waves. Wavy water. All right, and then our deltaT water. Looks like I used orange. Okay. And then, yeah, specific heat is going to be a 1. If we were to use that alternate form, looks like I used green for that, light green. Okay, but for the approach I started, the only two variables left that we need are going to be these two. The mmetal and the deltaTmetal. Right, oops, sorry, bumped the camera. All right, so let's go ahead and finish this problem. Okay. So I'll go to my previous sheet. This teal color I used here was for the QH2O, which is going to be that value, 525. So let's use this one. Okay. So here's my work doing the plug and chug. We have the Q of H2O being plugged in. That's that 525 calories we had earlier. Only 2 sig figs though. And don't forget that negative sign. All right, for the mass of the metal, I plugged in 44.02, which I had in red earlier. And then our temperature difference, okay, 24.2 minus 80, we did that already in advance. And then we got this result. All right, so the way I would have plugged this into my calculator. All right. Oh, and by the way, these negative signs will cancel. All right, like I said earlier, or I wrote earlier. If you have a we have a negative sign in this equation, but don't worry about it. Don't worry about the negative sign. The negative sign will cancel by either having a negative Q or a negative deltaT. All right. You'll always have a negative there or there, so the negative will always be canceled. The C of the metal will always be a positive value. Okay. All right. So with that said, let's do it. All right. So I'll leave it up to you whether you write negative signs in your calculator or not. You can recognize that these will already cancel and keep everything positive. Just be aware if you can use the negative sign. Some calculators, you have to use the so-called negative sign in the calculator. Not all of them will allow you to use the subtraction operation. Negative sign 525 divided by 44.02 times negative 55.8. Close parentheses. Make sure you use parentheses for the denominator if you're calculating it my way. All right, so 0.214 is the answer, but we can only go to 2 sig figs, so we say 0.21. All right, so here's my source, Chem-Libretex. I'll put a link for them in the description, and they have this nice specific heat capacity table, and we see that aluminum matches pretty good. All right, if we were able to have one more sig fig, we would have 0.214. And that's pretty close to the 0.215 over there. We can look at other candidates like copper, that's like less than half of aluminum's, iron less than half. And if we weren't like 100% sure if there's like multiple metals or materials with a similar specific heat, we could do some other experiment to figure out that it's aluminum. We could like calculate its density. And like a density you could do by like a displacement sort of experiment. Here, let me show that in a minute. Yeah, so like if we're trying to figure out a density, we could measure the mass of the block, and then we could put some water into a vessel, something preferably more accurate and precise than a beaker, but a beaker might work in a pinch for a large object. Fill it up with some water, enough to like cover the object, and record the initial volume. Let's say I was like at 100, and then I put it in, and it goes up by, I don't know, like 25 milliliters or something. So if it went up by 25 mils, then you would know the volume of that solid. All right, and then using a density, you can maybe confirm another property for the block and figure out what it is. But I will tell you, this is a piece of aluminum. All right, hope that helps, and let me know if you have any questions or comments. Thanks, take care.